All right, so we're going to keep working on our lovely finance stuff. Today, we're going to talk about what are called annuities and sinking funds. So either option, whether I'm talking about it, is going to be a periodic payment, whether that is a periodic deposit. So like I am putting in to an account the same amount every month, or I am drawing out of that account the same amount every month. So annuities are generally where you talk about, I want to put in the money for later. A sinking fund is where I have some amount and I'm going to then draw from that every month. You will see here that we have another lovely formula. And I do have on Blackboard, there is a entire like chapter 3 formula sheet. It is back under week 12. And it goes through all of the formulas that we have, what each variable represents. Pull that up for you quickly here. Looks like this. So all of the formulas are going to be there, along with some little like extra notes like, hey, if you're solving for t, that's where we log both sides, things like that. So we're down here for annuities and sinking funds. And then next week, we'll talk about loan amortization. This one has our future value, the periodic payment. They use I for the interest rate per period. So on the side, I put here, I is R over M, like we did last class. And N is the number of payments total. So that's going to be how many times a year times how many years, or that MT that we had talked about last class as well. So could also be rewritten as 1 plus R over M to the MT minus 1 all over R over M. All right, so we are going to start with just finding the future value, the easiest option of them all. So N is 20. I'm going to make 20 deposits of $500, earning interest at 0.03. And I want to find the future value. So future value equals payment 500. And then on top of the fraction, 1 plus the interest, 0.03, to the n power 20. Then I put a minus 1 all over that rate again. So 0.03. Any scientific calculator will work to solve these. So 500, and then I'm going to hit times, and I'm going to hit the fraction there so that I know that I'm going to type this as a fraction exactly as I see it. 1 plus 0.03, close to the 20, arrow out, minus 1, and then all over 0.03. I like Desmos just because it literally looks exactly like I typed it, or like I wrote it here on the side. So if I deposit $500 to 20 times, so just to show you here, I put 500 in 20 times. I deposited $10,000 of my own money, but due to interest and earning interest on those repeated deposits, I've now reached $13,435.19. You can always figure out how much interest you earned by taking your monthly or periodic payment times how many times you did it, and then subtracting that result. So I put in $1,000, I would earn $3,435.19 in interest. In order to accumulate enough money for a down payment on a house, a couple deposits $300 per month into an account paying 6% that's going to be compounded monthly. If payments are made at the end of each period, how much money will be in the account in 5 years? So again, I'm looking for the future. I'm going to put $300 in. 1 plus, now this one is telling me how frequently I'm compounding it. So 6% is 0.06 divided by 12. And that is 12 times a year for 5 years. So my exponent is going to be 60. I'm going to make that $300 deposit 60 times. Minus 1, put it all over 0.06 over 12. So then I'll go to my Desmos calculator here. Raise it to 60, arrow over, minus 1, all over 0.06 over 12. So at the end of my 5 years, I've now accumulated $20,931.01. Again, I could go back and figure out how much I put in. 300 times 60. I put in 18,000, so I earned $2,931.01 in interest. Any of the formulas we work with can be rearranged to be solved for another variable, right? And when we did early on, so if I know like distance equals rate times time, that's a common formula that you would see in, I want to say physics or something like that. I could rewrite this equation solving for R or T instead of D. And that's just a matter of using those opposite operations to move the variables to the other side to solve for the new one. So that is what was done to create this equation here. What they did was they took our future value equation and solved it for payment. So when I use this, the goal of this is kind of thinking of like a retirement. I want to have this money in the future. What do I need to deposit monthly to be able to get that value? Or how much can I can also use it for, if I have this much money, how much can I draw out every month for so many months or years or whatever? So it says our future value is 5,000. I have 15 deposits or withdrawals I'm going to take. Interest is 0.01. What is the payment that will get me to that value? So payment equals future, oops, sorry. Need to actually put in my future value. 5,000 times the interest rate, 0.01, over 1 plus 0.01 to the 15 minus 1. It's going to look similar to other problems, except that future value and payment have flipped spots, and the fraction is flipped as well. So it's a reciprocal fraction, and payment and future value have switched locations. $5,000 open, or so open fraction 0.01 over 1 plus 0.01 raised to the 15 arrow minus 1. In order to reach that $5,000 target, I would need to have payments of $310.62. SunAmerica offered an annuity that pays 6.35% compounded monthly. What equal monthly deposits should be made into this annuity in order to have $200,000 in 15 years? So my goal is again to find the payment. I want to reach 200,000. So this time my interest rate is 0.0635 over 12. So I'm going to have 1 plus 0.0635 over 12. 12 times a year for 15 years. 12 times 15 is 180 as my exponent. So 200,000 0.0635 over 12. Bottom of the fraction, 1 plus 0.0635 over 12 to the 180, then minus 1. So my monthly payment is going to be $667.43. And just for the sake of knowing what we did here, so 667.43, I did that 180 times. I only put into that account $120,137.40, which means almost 80,000 of that was the interest. This is very important to understand, that if you can make repeated deposits into an account like this, into an investment account, something you're not going to touch for many years like this, you can see how much that grows and how much interest you're actually earning. Bob makes his first $1,000 deposit into an IRA, earning 6.4% compounded annually on his 24th birthday, and his last $1,000 deposit on his 35th birthday. So he makes 12 equal deposits in all. That's the first half of the problem. So I'm going to look at that part of the problem first. So we are depositing $1,000 12 times, earning 6.4% interest. So that's going to give me, I can use that initial formula. Future value equals payment of $1,000, 1 plus 0.064. I don't have to divide it by anything because it's annually, for a total of 12 times minus 1 over 0.064. So I can see how much happens in those first 12 years. Now, I also have, I'm going to show you for this, there is also a Desmos calculator for annuities like we did with compound interest. So this one, it's called the future value. So I could use this equation here to do the same thing. You can see it's actually set up identical. So future value equals payment 1 plus interest rate to the power minus 1 all over the interest rate. So I could also use this guy here if I wanted to. 1,000.064 and a total of 12. All right, so he makes 12 deposits of $1,000, and at the end of those 12 years, he's up to $17,269.22. $17,269.22. So that is the first half of the problem. Now it says, with no additional deposits, the money in the IRA continues to earn 6.4% compounded annually until Bob retires on his 65th birthday. How much will be in the IRA when Bob retires? So now we're just going to basic compound interest. So, sorry, A equals principal, $17,269.22. 1 plus interest rate 0.064 compounded. So he stopped at his 35th birthday and kept it in there till his 65th birthday. So interest compounds 30 times. So let's see, 17,269.22. 1 plus 0.064 to the 30th power. So by letting that $17,000 sit for 30 years, he is now up to $111,050.77. So all you youngins in here, if you can set up an account like this, that you can deposit some money in now and just let it sit and not touch it. He literally put $12,000 into this account and it turned into $111,000. Okay, so think about your future. Will this be as much today as it is worth today? No, but it's still setting you up for a better future. Guarantee Income Life offered an annuity that pays 6.65% compounded monthly. If $500 is deposited into this annuity every month, how much is in the account after 10 years? How much of this will then be interest? All right, so I'm going to use our special little future value calculator for this guy, just to give us another practice. So we are going to deposit $500. The interest is 6.65 monthly. So that is 0.0665 over 12. 12 times a year times 10 years. You can actually type it as that, 12 times 10, or you could actually type in 120. And it will give us our answer right here, $84,895.40. $84,895.40. And that was 500 times 1 plus 0.0665 over 12 to the 120 minus 1 over 0.0665 over 12. And it asks how much of this was interest. So this is where we just go back. 500 was deposited 120 times. So 500 times 120. I put in $60,000. So if I take that away from the 84,895, so 84,895.40, subtract out that 60,000, 24,895.40 was the interest. A company estimates that they will need $100,000 in 8 years to replace a computer. If it establishes a sinking fund by making fixed monthly payments into an account paying 7.5% compounded monthly, how much should each payment be? All right, so I'm going to show you how to solve for a payment in our future value formula. So because our future value formula for annuities has future value, payment, number of payments, and interest, I could solve for any of those variables. So if we want to use this guy to help us with our payment, I want to have 100,000. The interest rate is 7.5, so 0.075 compounded monthly. So I'm going to divide that by 12. And then 12 times a year times 8 years. And you'll see here, this is the payment formula. Takes your future value times the interest all over 1 plus interest raised to the power minus 1. That means the monthly deposits need to be $763.39. Last question for today. I am going to show you how we would do this by hand, and then I'll show you in the Desmos calculator. You can afford monthly deposits of $200 into an account that pays 5.7% compounded monthly. How long will it be until you have $7,000? Round to the next higher month, if not exact. So 7,000 is my goal. 200 is what I can put in. 1 plus 0.057 over 12 to the 12 times t. I don't know what that's going to be, so minus 1. All over 0.057 over 12. A lot of math involved in this one. First thing I'm going to do is divide out the 200. That's going to give me 35 equals 1 plus 0.057 over 12 to the 12t minus 1 all over 0.057 over 12. Now, I am dividing by a fraction. So what I would need to do to get rid of it is multiply both sides by that fraction. Because anytime you divide by something, if you want to undo it, you multiply it. So I'm going to multiply 0.057 over 12 to both sides. If I take 35 and I multiply that by 0.057 over 12, I'm going to get 0.16625, and that is the full decimal. So I'm not rounding at this point. I don't want to round anything. Next, I would add 1 to both sides. So 1.6625 equals 1 plus 0.057 over 12 to the 12t. Now, we talked last class that when your variable is in the power, the way we get rid of that or move it down is by natural logging both sides. So I'm going to natural log both sides so that on the right-hand side, I can use that property that says if I natural log something to a power, the power can come down front. 12t times natural log 1 plus 0.057 over 12. I'm so close. I want to get t by itself. So the last thing I'm going to do is divide by 12 natural log 1 plus 0.057 over 12. I want to get rid of all of those other pieces. And then I would go to my lovely scientific calculator, and it's going to give me about 2.7 for t. Now, that is in terms of years. We'll figure out how much that is in months, but I'm also going to show you how our lovely Desmos calculator helps us with this process. So if I go back to the top here, it says I can solve for the number of payments. So I know I can put in 200. My goal is 7,000. And my interest rate is 0.057 over 12. And then this is going to give me my answer in terms of payments because it's all based off of how much I divided by. If I divided by my interest rate by 12, then I'm making 12 payments a year. I'm making my payments monthly. So this answer is rounded 33 months. And if you check and take 2.7 times 12, you will get that same 32.4, which rounds to 33 months. I like to show you by hand in the case that you're working on, let's say, a standardized business exam where you have to use just a scientific calculator and you have to be able to work through the formula, okay? But I also like to show you the tools that we have to help us do these faster rather than going through the by hand process when I don't need to do that. So those two Desmos calculators are there. And I will tell you, when I give you your test, I literally link the respective Desmos calculator to the problem. I'll specifically say, like, you can use this Desmos calculator to do this problem. Now, you have to understand how to use it. You have to know, am I doing future value, payment, number of payments, interest? Which one am I solving for? And then what value goes in where? So you still have to know how to use it, just like you would have to know how to use the formula. Do you have to use it? No. You are more than welcome to do these by hand if you choose to. I don't care either way. But that is where we are for today. So work on your homework for 3.2 and 3.3. Also make sure you work on that discussion board. If you haven't started that yet, you can work on that. That is due by Sunday. And then I only see you 3 more times.